All right, hello and welcome to this video lecture. So today we are doing day 2 of how hypothesis testing works, picking up on where we left off on Wednesday in class. So let's go ahead and get started. All right, so last time we had an exit ticket question of what are the two hypotheses that we test. The answer, of course, is the null and research hypotheses. Now remember, right, we talked last time about how you can have your personal hypothesis, what you personally think is going to happen, but statistically speaking, we're testing two hypotheses against each other, and that's the null and the research hypothesis. All right, homework number 13, then let's review what happened there. All right, so question 1, in an experiment, people are told to solve a problem by focusing on the details. Researchers want to know, is the speed of problem solving different for people who get those instructions compared to the speed for people who are given no special instructions? So part A here, state which two populations are being compared. Population 1 for this study example is people who are given special instructions, whereas population 2, people who are given no special instructions or people in general. Stating the research hypothesis then would be something like this. There will be a difference in problem-solving speed between people given special instructions and people given no special instructions. Part C of question 1 then, to state the null hypothesis. That would be something like this. There'll be no difference in problem-solving speed between people given special instructions and people given no special instructions. And then part D, explain whether your research hypothesis is directional or non-directional. In this case, it would be non-directional because it's not predicting the direction of the difference. For example, we're not comparing higher versus lower. We're not predicting higher versus lower speed between groups. We're just saying, hey, it could go either way. It could be higher, it could be lower. We're just saying there could be some kind of a difference. Question 2 then, same task with another example. So in this one, researchers want to know, do people who live in big cities develop more stress-related conditions than people in general? So part A, stating which two populations are being compared. In this case, population 1 is our people of interest, right? People who live in big cities, whereas population 2, people in general. And then part B, stating the research hypothesis. That would be something like this. People who live in big cities will develop more stress-related conditions than people in general. And this is, of course, really just mimicking the format of the question here, which says, do people who live in big cities develop more stress-related conditions? That's our research hypothesis. C, then, state the null hypothesis for this study. That'd be something like this. There'll be no difference in development of stress-related conditions between people who live in big cities and people in general. And then lastly, part D, explain whether your research hypothesis is directional or non-directional. In this case, it's directional because it stated the direction of the predicted effect, specifically that there would be more stress-related conditions for people in big cities compared to people in general. All right, now hopefully you guys are still using your metacognitive strategies. You might want to consider continuing to use them over spring break. Even if you just get out your notes and review once or twice over break, you'll do yourself a favor compared to if you don't think about stats at all over break. So something to consider. All right, and then today we're going to forge onward with how hypothesis testing works. So last time we talked about what hypothesis testing is. We talked about how, broadly speaking, there are 4 steps in this process. We talked last time about the first step in the process, generating the null and research hypotheses. We're going to pick up today talking about our next step. After we have our hypotheses, what do we do next? And that is the step of finding the cutoff score on the distribution of means. All right, now we talked about this last time, this sort of broad overview of how this process works. We want to know about the psychology of the population. Of course, we can't test the whole population, though, as we talked about in sampling and probability. Instead, we have to take a sample and test them in a well-designed research study. We usually find pretty small differences in our studies, like that example of getting 87% average with flashcards versus 83% average with rereading. That's way more common than either a really enormous difference or a really, really tiny non-existent difference. More likely, we have this sort of relatively small difference. And we have to know, is that a real effect of the independent variable, or is it just chance fluctuation due to individual differences? With this example, this 4% difference, it's hard to tell by just looking at it whether it's a real effect or if it's just chance differences. And that's why we need hypothesis testing. So here's what we're picking up today. We use a probability distribution to find a cutoff, at which point we're too unlikely to see our obtained result by chance alone. We do this using the distribution of means, and we do it using the characteristics of the central limit theorem, which of course we talked about with our M&M demo last week. All right, then at that point, if our sample data falls beyond that cutoff, that's when we get to decide that it's a real effect. So today we're going to pick up by talking about this idea of the probability distribution, finding a cutoff, at what point we're too unlikely to see that result just by chance. All right, so finding a cutoff score. We have to find a set of cutoff point on our comparison distribution, at which point the study's results were so unlikely to happen by chance that it's probably a real psychological effect. And that's what we're doing here in this step of the process. We're finding that cutoff point. It's important that we find this before we actually run the study and calculate the statistics, because we don't want to be biased in how we pick this cutoff point, right? We don't want to pick a cutoff point specifically so that our obtained results will be significant. That's a big problem in psych research, and we'll talk a lot more about that later in the class as well. But it's important that we set this cutoff point in advance so that before we ever run the study, we know what the cutoff is for us to decide that it's a real effect. All right, now we're finding this cutoff point on our comparison distribution. Specifically, our comparison distribution is the distribution of means. Now remember the distribution of means when we talked about it in sampling and probability with our M&M demo. It is all possible sample means drawn from the population. So that means that in our chocolate and happiness example, it's all sample means of happiness scores drawn from the population. Not just our chocolate eating people, right, but everybody. So specifically for this example then, it's the theoretical probability distribution of samples of happiness scores for everyone, not just our participants who ate chocolate. Now remember we talked about this last week. The distribution of means is always theoretical in nature because it's extreme. It would be really, really hard to try to make one manually. That would be basically impossible to do. In particular, when we're dealing with psychology variables, right, we don't actually have population data from which we could make this distribution of means. So instead, we theoretically construct it based on what we expect to be true. We'll come back to this idea in just a second here. All right, so the comparison distribution, right, specifically for this example, theoretical distribution of all samples of happiness scores for everyone. That makes it an infinite number of sample averages of happiness scores from the general population. That's what makes up our nice distribution here, the distribution of means, an infinite number of sample averages of happiness scores from everybody. Now, importantly, our chocolate eating sample in this study example is just one sample mean of happiness scores. So we're going to look to see where does our chocolate eating sample fall in this distribution. If our chocolate eating sample, if their happiness scores fall right around where everybody else's does, that's when we would say, chocolate doesn't really seem to have an effect. But if our chocolate eating sample falls way out in the tails of our population here, that's when we would say, oh, okay, it looks like chocolate's impacting happiness levels. That's the basic logic behind this part of the process. So we're going to see, are they about as happy as everybody else? If they're in the hump, we'd say, probably not a real effect. But if they're out in the tails, we'd say, oh, wow, they're way happier than most people, or they're way less happy than most people. That's when we conclude that chocolate probably does affect happiness. All right. Now, one way that you can think about it like this. The comparison distribution, we often say in statistics, the comparison distribution represents the population where the null hypothesis is true. In other words, it's the population's happiness in general. You can think about it as being like the null hypothesis is saying there's no difference after eating chocolate compared to the general population, right? That's what the null hypothesis says, that we're going to find no difference here. Our comparison distribution is all of our sample averages of non-chocolate eaters' happiness levels, right? It's not all chocolate eating samples, it's everybody's happiness levels. So if we find that there's in fact no effect, in that case, the null hypothesis is true. So the comparison distribution is representing that situation where the null hypothesis is true. This is what we have to compare our sample data against. If the sample data looks like the theoretical population data, so in other words, it falls in the hump, then the null hypothesis must be true and there is no effect. If our chocolate eater's happiness is no different than everyone's happiness, then chocolate doesn't affect happiness, in which case the null hypothesis is true. Therefore, the comparison distribution is representing the situation where the null hypothesis is true. But if our sample data does not look like the theoretical population data, so in other words, it falls in the tails, then that means the null hypothesis must not be true, and there is in fact a real effect. In that scenario, if our chocolate eaters are in the upper tail of happiness, then chocolate must make people happier. So ultimately, that's what we're doing here, right? We're deciding, is the null hypothesis true? Does our sample look like everybody else in this theoretical comparison distribution, in which case the null is true? Or does our sample not look like everybody else? It's falling in the tails in those rare unlikely scores, in which case the null hypothesis is not true. There must be a real effect. Now, I know that logic is a little bit confusing, so if you're like, what, I don't really get that, that's okay. If that doesn't help you to think about it like this, then don't think about it like this. But if it helps you to think about it as the comparison distribution being what happens if the null is true, it's what we would expect to see if the null is true, then in that case, use that to help you think about it. All right, so we talked about, right, we need to find a cutoff point on our comparison distribution, at which point the study's results were so unlikely to happen by chance that it's actually probably a real psychological effect. We talked about how the comparison distribution is the distribution of means, which again is all possible sample means drawn from the population. And importantly, we know the characteristics of the comparison distribution because of the central limit theorem. So thanks to the central limit theorem, we don't have to manually create a comparison distribution. Instead, we can theoretically construct it. In particular, we can estimate its shape, its mean, and its standard deviation. All right. Now, once we've identified our characteristics of our comparison distribution, so in particular that shape, mean, and standard deviation as per the central limit theorem, what we end up doing is we use that information to find a cutoff score on the comparison distribution, which represents the point at which scores are too unlikely to happen by chance alone. So this is where we're finding that cutoff score. Cutoff score is where the region of rejection begins. We'll talk more about this idea of the region of rejection in just a minute. Basically, our cutoff score is the point where it would be too unlikely to get that sample mean if the null hypothesis were true. So if you think about this in terms of our chocolate and happiness example, right? So let's say that the average happiness rating of people in general is 7 out of 10 with a standard deviation of 1. That means that in this sort of theoretical example here, say that we know that people in general score about a 7 out of 10 on their happiness scale with a standard deviation of 1. So in this case, we would know that this is true. The average happiness is 7 in the population. If our sample's average happiness after eating chocolate was also 7, that would then suggest that it's unlikely that chocolate affects happiness, right? If our sample is exactly the same happiness as our population, we'd say, they're just as happy as everybody else. Chocolate doesn't seem to be doing anything. But if we give chocolate to our sample and we get a different score other than 7, that's when we have to decide if it's extreme enough to be a real effect, right? If our sample's average rating is 7.4, compared to our general population happiness of 7, is that going to be extreme enough, right? So is that difference of 0.4, is that really suggesting that chocolate's increasing happiness, or is our sample just a little bit different from the population just by chance? What about then if our sample's average happiness was 9, right, compared to 7 for the population average? Is that extreme enough? This is why we have to set a cutoff score ahead of time so that we know at what point can we reject the null and say, yes, this is a real effect of chocolate on happiness. All right. Now remember this from sampling and probability. We talked about how if something very rare happens, it could be due to chance, but that's unlikely. It could be due to something else going on. So for example, if we flip a coin 100 times and it comes up heads every single time, that could happen due to chance, but it's incredibly unlikely. More likely, if we flip a coin 100 times and it's heads every time, we would suspect that the coin is rigged or perhaps it's two-sided. The same idea applies to psych research as well. So at some point, a sample mean is so far above or below the population mean that it's extremely unlikely that chance produced such an unrepresentative sample. Now remember, it's not impossible. Stats is all about probability. It's always possible that we have a very different score just by chance alone. So not impossible, but very unlikely, incredibly unlikely. Just like our example of getting heads, if you flip a coin 100 times, could happen due to chance, but way more likely something else is going on. That's the same logic that we're going to use when we're doing psych research. So if you think about this in terms of the chocolate and happiness example, a sample mean of 7.4 when the population mean is 7 is pretty close to the population mean, right? There's a pretty good chance that they just fluctuated by chance alone, right, because of individual differences, not a real effect of chocolate. But if the sample mean is 9 versus population mean of 7, that's a pretty big difference. Still possible that it's just a chance difference, but it's pretty freaking unlikely. So our cutoff score tells us when do we cross that line into the point where we can say, yeah, it's probably a real effect. Now we talked back in sampling and probability about a 5% cutoff, right? So a 5% cutoff, at which point we would decide that it's a real effect. So it would be like 8, 9, or 10 heads out of 10 flips. Cumulatively, that's a 5% chance of getting that with a fair coin. That's actually the exact percentage that we tend to use in psychology research. So in psychology, we're comfortable with a 5% probability that a score will be at least that extreme if the null hypothesis were true. Now that means that there's a 95% probability that the score is too extreme for the null hypothesis to be true. So it's too extreme of a score, too far out in the tails for there to really be no effect. So basically, you can think about it as being a 95% chance that there is a real effect. And that's pretty good odds, right? 95% chance that chocolate really is increasing my happiness, only a 5% chance that it actually does nothing. I would take those odds and I would eat chocolate the next time I wanted to be happy, right? Or think about it in terms of our flashcards example. If we have a 95% chance that flashcards is increasing grades by about 4% compared to rereading notes, I would take those odds, right? I would study with flashcards to give myself that opportunity to have a better score. So ultimately, these are pretty good odds. Now keep in mind though that if we surpass this cutoff, we make this cutoff and we say, okay, yep, we're out in the tail, that does not mean that we absolutely definitely do have a real effect. There is always that 5% probability that it just happened by accident. So if you look at the distribution on the screen here, right, that 5% cutoff located in the tail there, that tail still happens in the general population. So if you think about this, if this distribution is the distribution of means for people's happiness levels, even people who have not eaten chocolate sometimes will get sample means that are that extreme. So sometimes they'll be way above average or way below average just by chance alone. That means that whenever we do research like this, there is always a chance that we are wrong. So there's always a chance that it really was just an accident, an accidental fluctuation due to individual differences that produced that effect. Now we're going to come back to this idea of how there's always a chance that we're wrong. After we come back from spring break, we'll talk about the z-test, and then we'll talk about type 1 and type 2 errors. This idea of type 1 and type 2 errors, that's where we'll talk more about these issues with probability. But for now, just think about it as being 95% chance as a real effect, pretty good odds, hence why we tend to be comfortable with that 5% cutoff in psychology research. Now we call that 5% the region of rejection. So we said that a minute ago. Let's revisit this idea of the region of rejection and talk about what this means. If our sample data falls in this region, that means that we can reject the null hypothesis and say that we do indeed seem to have a real psychological effect. That's why we call this 5% the region of rejection. Once our sample mean from our study falls into this region, so like you can see on the distribution here, this red line 0.05, the rest of the tail there up to 3 and 4 standard deviations, that is the region of rejection. If our sample data falls there, that means that we get to reject the null hypothesis. And we can say, no, doesn't seem like there's no effect, instead seems like there is an effect, hence region of rejection. It's where we get to reject the null. The question then is, where do we actually put the region of rejection on the probability distribution? Now, there's actually two options for how we can do this depending on whether our hypothesis was directional or non-directional. Now, last time we talked about how deciding if your hypothesis is going to be directional or non-directional affects a later step in the process. This is where that comes back and affects our process. Now, if we're testing a directional hypothesis, so again, it's one where you're predicting the direction of the effect. You're saying it's going to cause an increase in the DV or a decrease in the DV, but you're predicting one or the other. That's when we use what we call a one-tailed test. In a one-tailed test, we're looking for an extreme result at just one end of the comparison distribution. That would be like if my research hypothesis was that eating chocolate would make people happier, would make people more happy. In that case, I'm predicting the direction. I think it's going to increase their happiness. That means I'm going to use a one-tailed test. I'm going to look for an extreme result at just the high end of my distribution. What you're doing when you're doing a one-tailed test is you're putting the whole region of rejection, so the whole 5% probability, in just that one tail. So either end, right, you could put it at the negative or at the positive end, but either way, the whole 5% is going in only one tail, hence one-tailed test. So again, that would be like our chocolate happiness example. If we're predicting that chocolate increases happiness, then we're really just looking for an extreme score on the positive end. We would pick the one-tailed test, the right-hand example of our two distributions on this slide. The one on the right, that would be our eating chocolate makes people happier directional hypothesis. So we put the whole 5% probability in just that one tail. If we then get a score with only 5% probability in that tail, we're going to think, okay, too extreme to have happened by chance. Instead, it seems to be a real effect of chocolate increasing happiness. So that's the directional hypothesis. You do a one-tailed test. If instead you're doing a non-directional hypothesis, then you do what we call a two-tailed test. Remember, a non-directional hypothesis where you say, could go either way. I'm just going to look for some change in my DV. In this case, you're looking for an extreme result at either end of the comparison distribution. That would be like our non-directional hypothesis, chocolate affects people's happiness. It does something. We're going to do a two-tailed test, put our 5% probability in each of those ends there. Specifically, we're splitting it in half. Split the region of rejection, so that entire 5% probability, split it in half and put half in each of our two tails. So that would be like our distribution here with 2.5% in the lower tail and 2.5% in the upper tail. So again, this is for a direction or non-directional hypothesis where we're saying some kind of an effect could go either way. We're looking for an extreme score in either end. We're not sure what the effect is, but we think there's going to be some effect, right? So our chocolate happiness example, if we're predicting that chocolate affects people's happiness, could increase, could decrease, then we're splitting that 5% probability and put half in each of our tails. So 2.5% in the right tail, 2.5% in the left tail. The important thing here is that in total, it's still only 5% probability. So I could not put 5% in the left tail and 5% in the right tail, because cumulatively, my region of rejection then would be 10% probability. And 10% is too high. We're not comfortable with a 10% chance that it just happened by accident. We only want a 5% chance. Hence why we split it in half and put half in each of our tails. That means if we get a score in either extreme end, we can consider it a real effect. Now, in psychology research, we actually typically use two-tailed tests. Even though we might be predicting a certain effect with our personal hypothesis, we typically will still use a two-tailed test. In fact, the vast majority of research articles that you'll read in later classes, pretty much all of those statistical tests are done with two-tailed tests. This is, again, the importance of the distinction between your own personal hypothesis and our statistical hypotheses. Personally, if I was going to do this chocolate study, I would expect that chocolate should increase people's happiness, right? But statistically, I'm still going to do a two-tailed test instead of a one-tailed to ensure that I am doing the best work that I can do. Now, the reason why, there's actually several reasons why it makes sense for us to do two-tailed instead of one-tailed tests. Probably the most important reason is because if we did a one-tailed test, but then we got an extreme score in the other tail, we cannot consider it significant. So if I did that chocolate example and I did a one-tailed test, I said, okay, chocolate's probably going to increase happiness, and I put my whole 5% probability, my whole region of rejection in the upper tail. If then I do that research, I give chocolate to my sample and I record their happiness, if then my sample's happiness is incredibly low, so if it's way, way lower than the population, even if it's way outrageously far in the left-hand tail or lower tail, I can't consider it significant because I don't have a region of rejection in the lower tail. Everything that's not the region of rejection is where you have to say, okay, there's no effect. So no matter how low that score is in this hypothetical example, no matter how low it is, I can't say it's a significant effect. I have to say, oh, chocolate did nothing to people's happiness. And we don't like that, right? We don't like being boxed in by that. It is not uncommon in psychology research for us to predict one thing and find the complete opposite. And you'll see those as you take other classes in psychology. There's tons of examples of totally counterintuitive findings, right, that are opposite of what you would usually predict. if every time we did research in psychology, if we only used one-tailed test, every time we got a counterintuitive finding, we'd have to scratch that study and say, oh, nothing happened, and try again with a two-tailed test in order to actually capture that effect, right? So we don't like the idea of wasting our time and our resources in psychology. Hence, we typically just do everything as a two-tailed test in order to make sure that we can catch those effects if they end up going opposite of what we predicted. So it makes sense for us to do two-tailed tests to make sure that if we do get an opposite effect, we can still consider it to be significant. Another sort of bonus of doing a two-tailed test is that if we split the region of rejection into both tails, it actually makes it a more conservative test. And by that I mean that the score in your sample has to be more extreme to fall in a 2.5% region of rejection, because again, we have that 2.5% on each side. So whichever direction your score actually goes, upper or lower, it has to be more extreme to fall in that smaller region compared to if I put the whole 5% on only one side. And we'll talk about this idea a little more detail when we come back from spring break as well. But basically the idea is it has to be farther out into the tail in order to fit into a 2.5% region of rejection compared to a 5%. That means it has to be a bigger difference, right? A bigger effect of our IV in order for us to consider that it's significant. So we like this bonus that it's a more conservative test. It gives us a little more confidence that it's really a real effect. In general, though, it's really a custom in psychology to use two-tailed tests for these reasons and for others. So most of the time, in vast majority of cases, the research that you read in your other classes or that you conduct in your research methods class, for example, will be with two-tailed tests. All right, so that actually wraps up our sort of second part of our process here, right? Last time we talked about the Nolan research hypotheses. We just finished talking about finding the cutoff score on the distribution of means. Once we've got our cutoff score, we're ready for our next step here. So after we've generated our Nolan research hypothesis and after we found the cutoff score on our comparison distribution, that's when we get to the bread and butter of this process. That's when we get to carry out the study, do the math, find the sample's mean, do our calculations here. We then get to compare our sample score against our comparison distribution, specifically against our cutoff score, and see does what happened in our sample, does that fall beyond the cutoff score in the region of rejection? If it does, we get to decide, okay, great, looks like there's a real effect, whereas if it does not, then we say, oh, bummer, looks like there's not a real effect. So if you think about our chocolate and happiness example, right, where we happen to know that the happiness rating of people in general is 7 out of 10, with a standard deviation of 1. If our sample average is 7.4, is that extreme enough, right? What about a 9? This step of the process is where we actually find that out. We give the chocolate to our sample, we record all of their happiness ratings after eating chocolate, we find the average of their happiness ratings, and then we get to decide where does that fall on our comparison distribution against the distribution of means. Does it fall with everybody else, in which case, chocolate doesn't seem to have an effect, or does it fall out in our tails beyond the cutoff score, in which case, well, great, looks like chocolate does have an effect. Now remember this, the first time we talked about this was way back in variability, right? We talked about how many inferential tests, the test statistic equals the difference between means divided by variability. So in most tests, we're comparing the difference between conditions against the variability of the data. The test statistic, what that is, depends on which inferential test you do. So for example, for a z-test, your test statistic is z. It's a z-score, specifically z-score for a sample mean. That's what we're going to pick up after spring break. We'll talk about the z-test, and we'll see how this fits into the process. For other tests, it's different. So for a t-test, your test statistic is t. We'll talk about that the week after we come back from break. For ANOVA, your test statistic is f, which we'll talk about a little later on. For correlation, your test statistic is r, etc., etc. So for each inferential test we do, it's a different test statistic, but ultimately they generally follow this basic outline here, comparing our difference between conditions against variability. Now again, we're going to talk in more detail about the specifics of the z-test after we finish talking through the hypothesis testing procedure when we come back from spring break, right? And then in part 3 of the class, we're going to talk about t-tests, ANOVAs, correlation, regression, etc. But ultimately, the math, even though the math changes for each inferential test based on what kind of data you have, you use that hypothesis testing procedure for every kind of inferential test. So again, we'll talk about this, we'll revisit this idea in more detail when we talk about the z-test, when we talk about the t-test, the ANOVA, correlation, regression, etc. We'll talk about how the math changes for each test and how the type of data you have influences which test you choose. But regardless of what specific inferential test you do, the hypothesis testing procedure stays the same for every kind of inferential test. So basically in part 3 and part 4 of our course, once we're finished with hypothesis testing in exam number 2, we're going to revisit this idea, this hypothesis testing procedure. That's going to be the same thing we use with the other inferential tests we do. All right, now remember this from sampling and probability. We talked about reporting probability. P equals whatever you calculated expressed as a proportion out of 1 instead of a percentage, right? So P equals a proportion. We talked about the example of the probability of rolling a 4 or lower on a 6-sided die. That probability is 0.67 or 67%. So we report that probability by doing lowercase p equals 0.67. When we calculate test statistics, like the z-score for a z-test or the t-score for a t-test, we also calculate p-values as well. The p-value is what tells us where the sample data falls on the comparison distribution. So for example, a high p-value closer to 1, so a higher probability, indicates that the data falls toward the hump of the comparison distribution. In other words, it's very likely to happen by chance and not due to a real effect of the IV. So in our chocolate and happiness example, right, that would be saying if we have a high p-value for a sample, it would be saying that, it's falling at the hump, it's where everybody else is on happiness already, no effect of chocolate. Whereas if you have a low p-value that's closer to 0, that indicates that the data falls toward the tails of the comparison distribution. In other words, that it's very unlikely to happen just by chance, and thus is probably due to whatever your IV was. Now, this idea might sound a little confusing. We're going to come back to this when we talk about the z-test and talk about this idea in a little more detail there. All right, now once you have the test statistic, what you do then is you compare it against the cutoff score. So you look to see, does it fall beyond our cutoff score in the region of rejection, or does it fall within the hump of our data? So if you look at the distribution on the slide here, right, we have a two-tailed test with our 2.5% probability in each tail. Our region of rejection is shaded in gray, whereas our hump is unshaded. Ultimately, what we're doing once we have our test statistic is we're deciding where does it fall. Does it fall in our shaded region, which is the region of rejection, or does it fall in the unshaded region, which is the hump of our data? This comparison of comparing the test statistic against the cutoff score lays the groundwork for the final step of the hypothesis testing process. The final step, of course, is to draw conclusions. Now, basically, right, the last part of the hypothesis testing procedure, after we've generated our null and research hypothesis, after we found the cutoff score on the comparison distribution, and after we've calculated our test statistic, is to draw conclusions, decide what did the study show? Was there a real psychological effect or not? So in the chocolate and happiness example, right, our last step here is drawing conclusions. Does chocolate have an impact on happiness or not? If your sample is more extreme than the cutoff score, so in other words, if it's in the region of rejection, it's in the tails of the comparison distribution. So if our sample score is more extreme than the cutoff in our region of rejection, that means that we reject the null hypothesis. Hence the term region of rejection, right? It's where we reject the null hypothesis. That means that the experiment had an effect. Woohoo, right? So in the chocolate and happiness example, if our sample score is more extreme than our cutoff score, we'd say, okay, look, chocolate does have an effect on happiness. If, however, our sample is not as extreme as the cutoff score, so if it's not in the region of rejection, instead it's in the hump of the comparison distribution, that's when we say that we fail to reject the null hypothesis. So if it's not in the region of rejection, we cannot reject the null. Instead, we say that we fail to reject the null. Bummer, no effect, results are inconclusive. Now, this is one of those little quirky things about statistics in psychology. We don't say that we accept the null hypothesis. Sometimes we do, but really the true way that we say this is we fail to reject the null. And that's funny because it sounds like a triple negative, right? We don't reject the idea that there's no difference. Ultimately, though, this is just saying we're accepting the null, we're retaining the null, we're saying, looks like the null is true after all. It's just a terminology thing that we say fail to reject the null. So just keep that in mind. All right, now a little more detail about rejecting versus failing to reject the null. If we reject the null hypothesis, that means that our results support the research hypothesis. Importantly, though, we can't ever really prove anything to be true. We talked about earlier, there's still that 5% probability that it was chance, right? There's still a possibility that our sample just happened to fall in that very extreme high tail or very extreme low tail just by chance alone, because those scores do happen in our comparison distribution, right? So there's still a 5% probability that it was just chance. That means that we can't ever prove anything to be true, so we stick with more tentative language. Instead of saying the results proved our research hypothesis to be true, we say that it supports our research hypothesis. This is a surprisingly important terminology thing. In terms of psychology research, and really any research, nothing ever really gets proved ever, because we never know for sure, right? We don't have access to that ultimate truth that tells us whether there's a real effect or not. So really, as a psych major, you should probably just erase the word prove from your vocabulary, right? It doesn't really have any place in statistics or in psych research at all. Instead of proving, we're supporting our research hypothesis. Now, if we fail to reject the null hypothesis, then we would say that our results did not support the research hypothesis. But we don't know why. Was it a bad study design? Do we not have enough power to detect a real effect, right? Maybe there's something wrong with how we operationalize the variable, with how we measure it in our study. Maybe there's something weird going on with the time of day, right? There's all these reasons for why we might get null results, for why we might have to fail to reject the null hypothesis. So again, if we fail to reject the null, it doesn't necessarily disprove the hypothesis, right? So we don't say that we've disproved the research hypothesis. We don't say that we've proved there's no effect. Instead, we just say that our results did not support the research hypothesis. So again, along with this idea of erasing the word prove from your vocabulary, there's never any proving of anything going on in psych research or in any other research, because it's all based on statistics, it's all based on probabilities. We're saying we're pretty sure there's a real effect, or we're pretty sure there's no real effect, but we never know absolutely for certain. So this idea of drawing conclusions, right, never proving anything true, never disproving anything or proving anything not to be true, think about this like you would think about juries in criminal cases. If you're a jury member on a criminal case, you never know for sure whether someone committed a crime, right? Because we're not that person. So we don't know for sure whether something happened. And in a lot of criminal cases, right, you're dealing with evidence, like, maybe there's suggestive text or there's, DNA, stuff like that. But none of that is definitive, right? That's why jury members don't have to be definitively sure that the person is guilty or not guilty. They need to be beyond reasonable doubt. So there has to be enough evidence that they say, pretty sure this person committed the crime, or pretty sure this person did not commit the crime. They have to be beyond reasonable doubt, but they're never 100% sure. That's the same idea we're doing in hypothesis testing with psych research. We're never going to know the true population results because, like we talked about last week, we could never possibly measure the entire population. It's just impossible. So we're never going to know for sure, but we can be beyond reasonable doubt. That's the idea of the 5% cutoff, right? That's where it gets us beyond reasonable doubt. 95% chance there's a real effect. That gets us beyond reasonable doubt. Again, we're never proving or disproving. We're never 100% sure, but we're beyond reasonable doubt. We think, pretty sure it's a real effect, or pretty sure it's not a real effect. So I know that might sound kind of unsatisfying to say that we never really know anything for sure, but it's just how psychology research works. Now, when we reject the null hypothesis, when we decide, okay, it looks like there's a real effect, we then say that the finding was statistically significant. So for example, in our chocolate and happiness example, the results were statistically significant, supporting our hypothesis that eating chocolate makes people happier. Now, usually when we do research studies, we typically kind of secretly want to show that there's a real effect, right? So our personal hypothesis is usually that there's a real effect. That's usually pretty exciting. But again, like we just talked about, there's always that 5% chance that it really just happened by accident. So important next step then would be to replicate that finding. So replicate meaning do it again. So do it again with a new sample, do the same process over again. If you find a significant result again, so if you reject the null hypothesis with your second sample, that means now you have 2 instances of a significant effect, a real effect. That gives us more confidence, right? That we weren't just that 5% happening by accident. If we get the significant effect twice in a row, we're a little more confident that it really is a real effect after all. If you fail to reject the null hypothesis, so if we say, looks like the null is true after all, that's when we say the finding was not statistically significant. So for example, the results were not statistically significant, indicating that eating chocolate does not seem to affect people's happiness. That's usually a bummer because usually we're not trying to find null results, right? Usually we think that there's a real effect, but like we just talked about, it's hard to tell the reason for null results, right? So maybe revamp the study, try it with a slightly different methodology, try it with a new sample, try it again. If we fail to reject the null hypothesis twice, so if we find no effect twice, then we have more confidence that there really is no effect after all. Now, one important thing here about terminology in statistics and in psych research is this word significant. In psychology, when we say the word significant, we really only mean in the statistical sense of rejecting or failing to reject the null. So if you want to say that something is an important new development, you wouldn't call it a significant development because that's going to confuse people and make them think that you're talking about statistics. So really, you should only use the word significant as psych majors in your psych vocabulary. Only use significant to refer to statistical significance. If you're thinking about sort of like general importance, use the word importance instead. So it's a terminology thing for you to think about. Significance really just means in the statistical sense. Now, ultimately, this whole process gives you a yes or no answer about whether your psychological effect seems to be real or not, right? That's one of the big benefits of hypothesis testing, is that if we go through this procedure, it gives us a yes or no answer. But a very common mistake, especially among people taking the stats class for the first time, is to get that yes or no answer of saying significant or not significant and then stop. So that would be like if we take our chocolate example saying, okay, there's a significant difference in happiness scores based on chocolate. Or to put a new example saying, oh, there's a significant difference in cult members' attitudes after their beliefs were challenged. And that's a problem. So if you just get this significant or not and stop, it's a problem. If I went out into the hallway right now in Hart Hall and I told people there's a significant difference in cult members' attitudes after their beliefs are challenged, there's a big problem here. And the problem is that we don't know what the difference was. If we take that cult member example, if we challenge people's beliefs, do their beliefs get stronger or do they get weaker? Could go either way, right? If I don't interpret the direction of that effect, then my reader, if in a research article, or my listener in the hallway, doesn't know what the finding actually is. They have to guess which way it goes. And that's not good, right? Because in your research study, you have the answer of which direction it went, right? You don't want your readers or your listeners to have to guess what happened. So statistics are critical in psychology, but even more important, you have to accurately interpret what the numbers are actually telling you. That's kind of the last part of our process here of drawing conclusions. So the last step in the hypothesis testing procedure then is to interpret what really happened in the study. Beyond just whether there was a statistically significant difference or not, what actually happened if there was a significant effect? So did the IV increase the DV or did it decrease the DV? Right? So you need to know what actually happened. Did chocolate increase people's happiness or did it decrease people's happiness? Now, an important note here is that we're actually going to be departing from the vague language of our non-directional research hypothesis. Right? We needed our research hypothesis to be vague to use a two-tailed test, but if we find a significant effect, now we get to depart from that vagueness. We get to interpret what the direction of the effect actually is. So although your research hypothesis is typically pretty vague and non-directional, once you have a significant effect, now you need to drop that vague language, and now you need to say what actually happened in your study. All right, so it's pretty simple what to do if you are failing to reject the null. So if you do your study, you find, okay, didn't get to reject the null, I have to say I'm not statistically significant. If you fail to reject the null, it means there's no psychological effect, and therefore there's no need to interpret any directionality. So if there's no effect of chocolate on happiness, then you don't have to say whether it increased or decreased happiness because it didn't do either, right? It did nothing to happiness. So for example, in the chocolate and happiness example, you would say that chocolate did not have a significant effect on happiness. Basically, if you fail to reject the null, you get to just restate the null hypothesis since that's the one that you supported, that's the one that you found to be true. So if you're failing to reject the null, you don't have to do anything with directionality. You can just say, there was no effect of chocolate on happiness. However, if you rejected the null, here's where you need to interpret the directionality. So you need to say what the direction of the effect was. So a little more effort is required here. Here's what you do in order to say what the direction was. You have to look back at the raw scores for the sample mean and the population mean, and you have to determine was the sample mean higher or lower than the population mean. So you have to look back at the means, right? The sample average and the population average, and you just say which one is higher. If your sample average is higher than your population average, then you say, okay, great, your IV increased your DV. But if your sample average was lower than your population average, you say, okay, great, your IV decreased the DV. If you think about the chocolate and happiness example, right, if a population happiness is 7, and if your sample's happiness is 9, if you went through the hypothesis testing procedure and you found significant effect, then your sample average of 9 is higher than your population average of 7, which means that chocolate is increasing people's happiness. So in that chocolate happiness example, you would say chocolate significantly increased our participants' happiness. If, however, you went through this process, your sample average was 5 and your population average was 7, right? In that case, your sample average of 5 is lower than your population average of 7. If that's a significant effect, right, through your hypothesis testing procedure, then you would say, okay, my IV decreased my DV. If it was chocolate and happiness, chocolate decreased participants' happiness. Now, this is a little bit of a complicated idea. One of the homework questions that'll be due the Monday after spring break is going to give you practice with this step of interpreting the direction of the effect. All right, so then in our last step of hypothesis testing here, we're deciding whether to reject the null or whether to fail to reject the null. And then if we rejected the null, found a real effect, then we interpret the direction of that effect. Ultimately, this entire sort of fourth step in our process, ultimately what we're doing here is drawing conclusions about the population based on the results of the study. And again, right, that's the purpose of inferential statistic. Hence, this is the important last thing to do in your hypothesis testing procedure, is to say, okay, here's what's likely to be true of the population based on what happened in our sample. If you think again about the chocolate and happiness example, with this study, this hypothetical study, we want to know whether eating chocolate makes people happier, not just in our sample, but in the population at large, right? We don't just want to know, does eating chocolate make our sample happier? We want to know, does eating chocolate make people happier? So if we fail to reject the null, so if we say, looks like there's no effect, then that means chocolate must not make people happier. That means that if we gave a random new group of people chocolate and had them eat it, we probably won't see a difference in their happiness either. So again, we're going beyond the sample here, right? We're going to the population. Hence, inferential statistics, we're using our sample to decide what's likely to happen in the population as well. If, however, we rejected the null and we said, there's a real effect, then chocolate does affect happiness, that means that if we gave a random new group of people chocolate and had them eat it, we would expect their happiness to change as well. Would it make them more or less happy? That's what we have to interpret based on the study's results, right? But again, we're going beyond the sample onto the population of saying, okay, what happened in the sample is indicative of what happens in the population more broadly. Again, that's the purpose of inferential stats, to say what's likely to be true of the broader population. All right, so that wraps up our discussion of the process of how hypothesis testing works, right? So we want to know about the psychology of the population, but we can't test the whole population, so we take a sample and test them. We usually find pretty small differences, so we have to have some mechanism of knowing whether it's a real effect or just chance fluctuation. That mechanism of making that decision is hypothesis testing, right? Ultimately, we're using a probability distribution to find a cutoff score, at what point we're too unlikely to see that just by chance alone. And then if our sample data falls beyond that cutoff in the unlikely scores, that's when we get to decide that it's probably a real effect of the IV and not just chance. We talked about this on the first day of hypothesis testing, right? This procedure follows these 4 broad steps, ultimately gives us a yes or no answer, whether there's a real effect. And we talked about how it's the same logic for all different kinds of hypothesis tests. The procedure and the math change a little bit for each test. That's because each different test, like a t-test or a ANOVA or a correlation, involves different types of data. But the logic of hypothesis testing is the exact same for everything. So we're always using this inferential procedure to determine whether we have a real effect, no matter what kind of data we have, no matter what kind of test, what specific test we're using. All right, now when we come back after spring break, we're going to pick back up with this using the z-test as an example of the whole problem, and then we'll talk about type 1 and type 2 errors as well, and then we'll take exam number 2 and move on to part 3 of the class where we talk about commonly used inferential tests. All right, now let's talk a little bit about the homework. So homework number 14 is going to be due Monday, March 18th after spring break. That means it's due by 9:05 a.m. Monday, so before we start our next day of material. So be sure this is on your radar to either do it right now and turn it in, or be sure it's on your to-do list to do it over spring break and turn it in by Monday morning. Question number 1, when the result of a hypothesis test is significant, it's wrong to say that the result proves the research hypothesis to be true. Why? Question number 2 is about drawing conclusions. So when we're drawing conclusions about the results of a research study, we need to be clear and specific about what the study showed. One important part of this process is to interpret the direction of the effect if the result was statistically significant. So for each of the following possible outcomes of the chocolate and happiness study, your job for question 2 is to write a sentence or two describing the direction of the result. So in other words, what was the actual effect of chocolate on happiness? A hint for this is to read each scenario carefully before answering. So scenario A, scenario B, scenario C, scenario D, and scenario E and scenario F. For each of these scenarios, your job is to write a sentence or two interpreting the direction of the effect if appropriate. All right, and then question number 3, kind of broader, big picture question here. We've been talking about the process of hypothesis testing. What are the 4 steps of the process, broadly speaking, and what must the researcher do during each step of the process? Now, a hint for this question in particular is to try to do this without looking at your notes. If you don't remember some of the steps, then you can take a look at one of the slides that lists the whole process, right? We have those at the beginning and the end of these slides here. And then write the descriptions of what each step involves, right? Everything you can think of that's involved for each of the steps. You can use this as a really good metacognitive activity where you think about what you've learned so far. So think about what the process of hypothesis testing is, what's happening in each of the steps. Use this as a tool to reflect on what you've learned. All right, and then today's exit ticket for the video lecture is one question here. Why do psychologists typically use two-tailed tests? Now, we're not having this as a regular class, so there's no Socrates for this. What you can do is include this exit ticket in your homework submission to earn your 1 exit ticket point for watching the video lecture. So basically, when you're submitting your homework, you can include your answer to the exit ticket at the beginning or the end of your homework within the same document, for example, and that's how you'll earn the exit ticket for this video lecture. All right, that's it for today for this video lecture. Let me know if you have any questions about anything. Otherwise, be sure to submit your homework with the exit ticket included before class on Monday after spring break. And I hope you all have an excellent spring break. Enjoy, sleep in, relax, and all that good stuff. I will see you the week after spring break.